operation of electronic brake control systems. Figure 1. ABS helps the driver avoid accidents in a panic stop situation by maintaining steering control of the vehicle. ABS systems use a computer that monitors the speed of each wheel as the brakes are applied. If one or more wheels begin to lock up, the computer sends electrical signals to solenoid valves that momentarily hold or release hydraulic pressure to that wheel until it speeds up and starts rolling again. Once that happens, the computer allows hydraulic pressure to be applied to that wheel again, slowing it down. This process is repeated very rapidly as the vehicle is brought to a stop. Because the tires remain in rolling contact with the road surface, the vehicle can be steered, allowing the driver to maintain directional control, steerability. Figure 1. These actions are completely dependent on the driver applying pressure to the brake pedal. Although the basic ABS system does a good job of managing the braking effort of the driver in a panic stop situation, it is limited to using the hydraulic pressure the driver exerts on the system. This means that the standard ABS system by itself cannot increase the hydraulic pressure in the ABS system, nor can it apply hydraulic pressure separate from the driver. As long as the driver is exerting firm pressure on the brake pedal, ABS can work fully. Figure 2. If a wheel is slipping, the TCS system applies the brake pressure to the slipping wheel. This causes torque to be sent to the wheel with more traction. The second generation EBC system was the traction control system, TCS. With the addition of a high-pressure pump and a few isolation valves to the basic ABS system, manufacturers found that they could assist the driver in minimizing wheel slip while the vehicle is being accelerated. This is especially effective on slippery road surfaces such as gravel, snow, and ice. In most vehicles, the vehicle's traction is only as good as the traction on the tire with the least traction. So if one tire is on a patch of ice, the vehicle may not have enough traction to move, and will ultimately become stuck. The TCS system applies brake pressure to the slipping tire, which causes more of the engine's torque to be transmitted to the wheel or wheels with the most traction. Figure 2. If necessary, the TCS system can also request that the engine's powertrain control module reduce the power output of the engine to further enhance traction. These actions are controlled by the PCM and do not require any input from the driver. A. B. Figure 3. A. Understeer condition. B. Oversteer condition. The next generation EBC system was the Electronic Stability Control, ESC, system. ESC takes the ABS and TCS systems one step further. By adding sensor information regarding the driver's directional intent, from the steering wheel position sensor, and sensor information regarding the vehicle's actual direction, from the yaw sensor, the EBC module, EBCM, can detect the start of an understeer, oversteer, or potential rollover condition. Understeer and oversteer are conditions that happen when a vehicle is traveling too fast for a particular corner. During understeer, the vehicle's front wheels are turned more sharply than the vehicle's path. Figure 3. The front tires are actually sliding somewhat sideways toward the outside of the corner. The greater the understeer, the more the tires slide. Understeer is also referred to as push, as in the vehicle is pushing in the corners. Oversteer is just the opposite. It occurs when the vehicle is turning more sharply than the front wheels are being steered. This happens when the rear tires are sliding sideways toward the outside of the corner. Oversteer is also referred to as loose, as in the vehicle is getting loose in the corners. The rear tires lose adhesion while cornering during oversteer. Most passenger vehicles are designed to have a bit of understeer because this condition is easier for a driver to recover from than an oversteer. Using information provided by the sensors of the ESC system, plus the wheel speed sensors, the EBCM monitors the stability of the vehicle, and can command individual brakes to be applied and request decreased engine torque, as necessary. For example, if a vehicle is traveling too fast around a right-hand corner, and the front wheels are starting to lose traction, understeer, the control system can apply the right rear brake to help pivot the vehicle around the right rear tire. This assists the vehicle in turning, and at the same time slowing the vehicle slightly. If additional measures are needed, additional brakes can be applied, and the engine torque reduced. The control system performs these functions automatically without any driver input other than steering the vehicle in the desired direction. Technician tip. It is important for customers to know that ABS, TCS, and ESC are not guarantees of avoiding an accident. These systems are designed to help drivers who are driving in a responsible manner to avoid an accident. Drivers can easily exceed the ability of these systems. You are the automotive technician. A longtime customer brings his 2012 Ford Explorer into the shop to get his brakes inspected. He claims that the brake pedal pulsates when he applies the brakes. You ask him if he has had any recent work done on the vehicle. He explains that he recently had new tires put on. He also explains that after leaving the shop, a car pulled out in front of him, and he had to lock up the brakes to avoid hitting him. He was startled by very heavy brake pedal pulsations. He says that ever since then, the brakes have a small pulsation that seems to be getting worse. He is wondering if there is a problem with the anti-lock brakes. 1. Is there a problem with the ABS system? What will you say to the customer? 2. What do you suspect is causing the pedal pulsations, and how did it occur? 3. How would you diagnose a problem when the ABS warning lamp is illuminated? 4. In what two primary ways does traction control reduce wheel slip? Anti-lock braking system overview. Figure 4. Typical ABS system. The ABS system is designed to prevent wheels from locking or skidding, no matter how hard the brakes are applied or how slippery the road surface, to maintain steering control of the vehicle and shorten stopping distances. The primary components of the ABS braking system are shown in Figure 4 and listed here. Figure 5. A hydraulic control unit, HCU. ABS master cylinder. Creates hydraulic pressure for each of the two hydraulic brake circuits. Power booster. Boosts driver brake pedal force on the master cylinder. EBCM or electronic control unit, ECU. An onboard computer that is programmed to monitor sensor data and send output control signals to electronic solenoid valves, which modify brake pressure to individual wheel brake units. Hydraulic control unit, HCU, or modulator. Contains electric solenoid valves controlled by the EBCM to modify hydraulic pressure in each hydraulic circuit. Figure 5. Most systems also contain an accumulator to store brake fluid under pressure. Wheel speed sensor, a device that monitors wheel speed and sends that signal to the EBCM. Brake switch. An on/off switch mounted at the brake pedal that informs the EBCM whether the driver is applying the brakes. The EBCM may be located inside the vehicle or mounted near the HCU, or it could be integrated into the HCU. In many cases, it is a separate module from the powertrain control module, and may be part of the vehicle's body control module, BCM. The body control module is the computer that controls the electrical system in the body of the vehicle. The EBCM receives input signals from the ABS sensors, compares these data to information stored in its memory, decides what actions are necessary, and sends output commands to the HCU. The HCU or modulator is connected in line with the brake lines between the master cylinder and the wheel brake units. It houses electric solenoid valves that control the flow of brake fluid to each wheel. The HCU receives operating signals from the EBCM to control the brakes under ABS conditions. The power booster and master cylinder assembly is mounted on the firewall. In most current applications, these components operate similarly to non-ABS power boosters and tandem master cylinders. Some manufacturers use a portless master cylinder to allow brake fluid to return to the master cylinder reservoir more easily than a master cylinder fitted with a compensating port. When the brakes are operating without ABS action, the brake pressure is controlled by the driver's foot pressure, which is assisted by the power booster. In other words, the ABS system only affects brake pressure when one or more wheels are starting to skid. Figure 6. A wheel speed sensor and tone wheel. Figure 7. An oscilloscope pattern from a wheel speed sensor. The wheel speed sensor consists of a tooth tone wheel, or tone ring, that rotates with the road wheels, and a pickup assembly that generates a speed signal. The wheel speed sensor is located near the wheel hub in many applications. Figure 6. The wheel speed sensor sends to the ear BCM an electrical signal that varies with the speed of the wheel. Wheel speed sensors can be variable reluctance sensors, magnetic induction, generating an analog AC sine wave signal. Figure 7. Wheel speed sensors can also be of the magnetoresistive or Hall effect type, generating a digital square wave signal. These signals can be used by the ear BCM to determine the speed of each wheel. We cover the operation of these sensors in much greater depth in the ABS components section. Anti-lock braking system operation. When the ignition switch is turned on, the ABS controller illuminates the yellow ABS warning lamp and performs an automatic self-check of the system. If the system check passes, the controller will extinguish the warning lamp, indicating to the driver that the ABS system is functional. Some ABS systems perform an additional self-check once the vehicle is traveling more than approximately 3 to 5 miles per hour, 4.8 to 8 kph. Failures in the ABS system cause the controller to illuminate the ABS warning light in the instrument panel. If the light is illuminated, the ABS system is shut down and doesn't operate. As the wheels start to turn, the wheel speed sensors generate small electrical signals and send them to the ear BCM. When the brakes are applied, the wheel's rotational speed is reduced. As the speed changes, the signal sent to the ear BCM changes in like manner. If the control unit detects that a wheel might be slowing too quickly and starting to lock, it sends output signals to the appropriate solenoid valve in the HCU to modify the hydraulic pressure to the affected wheel brake unit. Let's explore how that works. Principles of ABS braking. Braking force and the tendency of the wheels to lock up are affected by a combination of factors such as the friction of the road surface, the type, condition, and loading of each tire, and the difference between the vehicle's speed and the speed of the wheels. It should be noted that maximum traction happens with approximately 10 to 20% tire slip. Thus, maximum braking traction occurs when the wheels are rotating 10 to 20% slower than the vehicle speed. In the same way, maximum traction during acceleration occurs when the wheels are rotating 10 to 20% faster than the vehicle speed. At the same time, traction falls off quickly above approximately 20% wheel slip, which is why ABS is so effective. It allows just enough slip to keep the tires at close to their maximum traction. It does so by rapidly modulating the hydraulic pressure in the vehicle's brake system. During normal braking, as the rotational speed of each wheel falls equally, no ABS intervention is needed. In this condition, the EBCM does not energize the solenoid valves in the hydraulic unit. The master cylinder hydraulic pressure is applied to the wheel brake units, and the ABS is not involved. However, even though the ABS is passive during normal braking, the EBCM is constantly monitoring the speed of each wheel, looking for any wheel that begins to decelerate more rapidly than any of the other wheels. Figure 8. Hydraulic control unit solenoid valve arrangement for modulating ABS hydraulic pressure. If one wheel speed sensor signals more severe wheel deceleration, which means the wheel is beginning to slip, the EBCM sends current to the appropriate solenoid valve. Figure 8. The first level of valve action isolates the brake circuit from the master cylinder. This stops the braking pressure at that wheel from rising and keeps it constant. If the wheel speed sensors indicate that the wheel is still decelerating too rapidly, the EBCM commands the appropriate solenoid valve to release braking pressure. The solenoid valve opens a passage from the brake circuit, releasing the hydraulic pressure to that brake unit. Brake fluid is released from the specific brake circuit back to the master cylinder. Pressure in the brake circuit is reduced so that the wheel is not being braked. If the wheel speed sensors indicate that reducing the brake pressure is allowing the wheel to roll again, the EBCM de-energizes the solenoid valves. This lets the hydraulic pressure from the master cylinder be applied to the brake again. This cycle repeats itself at up to 16 times per second. It is normal in an ABS system for the valves in the HCU to keep changing position as they modulate the brake pressure that is being applied. These changes in valve position normally cause rapid hydraulic pulsations, which on some vehicles can be felt by the driver through the brake pedal. The solenoid valves also make a fairly loud clicking noise as they cycle on and off. Technician tip: drivers should be taught to expect ABS brake pedal pulsation when in a panic stop. Some drivers who have never experienced this actually let up on the brake pedal because of the rapid pulsations and accompanying noise. When in a panic stop, drivers should push hard on the brake pedal and not let up until the vehicle is stopped or out of danger. Brake-by-wire systems are not subject to this brake pedal pulsation situation because the brake pedal is not part of the hydraulic system. ABS components. ABS master cylinder. Figure 9. Non-integral and integral master cylinder assemblies. ABS master cylinders come in two major configurations, integral and non-integral. Figure 9. Integral ABS systems are mostly found on older vehicles. They combine the tandem master cylinder, HCU, and power booster in one unit. The power booster consists of a high-pressure electric pump and accumulator that operates the integrated master cylinder. Brake fluid passes from the master cylinder portion of the assembly to the HCU portion, where pressures are modified by the computer-controlled solenoid valves. Non-integral ABS systems use a fairly standard tandem master cylinder and a typical vacuum or hydraulic power booster. The booster assists the driver in applying force to the master cylinder. The master cylinder sends fluid under pressure to the HCU, which is a separate assembly that is installed in line with the brake lines between the master cylinder and the wheel brake units. If the pressure has to be modified, the computer-controlled solenoid valves in the HCU will carry out the commands. Purpose and operation of the ABS master cylinder. Figure 10. Portless ABS master cylinder. Non-integral ABS master cylinders are usually identical to non-ABS master cylinders. They both use primary and secondary pistons in a common housing with a common bore. Some of these master cylinders utilize a portless ABS master cylinder design, which does not use a compensating port on the secondary circuit. Instead, the secondary piston incorporates a center valve. Figure 10 that controls the opening and closing of a supply port in the piston. At rest, the supply port is open and connects the reservoir with the front brake circuit. The primary piston still uses an inlet port and a compensating port, therefore, the portless design is only used on the secondary circuit. When the brake is applied, the primary piston moves and closes its compensating port. Fluid pressure in the primary circuit rises. It acts with the primary piston spring to move the secondary piston forward, closing the center valve. Pressure builds in the secondary circuit, keeps building in both circuits, and applies the brakes in both circuits. If braking conditions are such that the hydraulic modulator must return brake fluid to the master cylinder, then, for the front brake circuits, brake fluid is returned to the front section. This forces the secondary piston back against the force of the primary piston spring and the rear brake pressure. If enough brake fluid returns, the center valve opens and allows the brake fluid to return to the master cylinder reservoir. If brake fluid is returned from the rear brake circuit, the secondary and primary pistons tend to be forced apart, which generally moves the primary piston rearward. If it travels far enough, brake fluid will return to the reservoir through the compensating port. The amount of brake fluid that returns to the master cylinder is determined by the degree of anti-lock braking control. With as many as 16 ABS control cycles per second, the rapid changes in hydraulic pressure cause brake fluid pulsations to be sent back to the master cylinder. These pulsations can be felt by the driver at the brake pedal. Control valve operation. Figure 11. A. Apply. B. Hold. C. Release. In a standard ABS system, the HCU houses electrically operated hydraulic control valves, solenoid valves, that control brake pressure to specific wheel brake circuits. Each separate hydraulic circuit within the HCU has one or two solenoid valves that provide three operating conditions: apply, hold, and release. Figure 11. During the apply mode, the solenoid valves allow brake fluid to freely flow through the HCU hydraulic control circuit to the specific brake circuit. In this case, the driver is in full control of the brakes through the master cylinder. In the hold mode, a solenoid valve isolates the master cylinder from the brake circuit. This prevents brake pressure from building any further. The brake pressure to the wheel is held at that level until the solenoid valve is commanded to change its position. In the release mode, a solenoid valve releases, dumps, the brake circuit pressure to the wheel, allowing it to start rolling again. The solenoid valve opens a passage back to the accumulator, where brake fluid is stored until it can be returned by an electric pump to the master cylinder reservoir. Notice that the brake pressure is held or dumped even though the driver is applying the brake pedal. Technician tip: many, but not all, HCUs are sealed units and cannot be serviced. If you are working on a vehicle with a sealed HCU and it is faulty, it will have to be replaced. This can be quite costly. Operation of the hydraulic control unit. The ABS control module, or EBCM, sends commands in the form of electrical signals to the HCU. The HCU executes the commands, using one or two solenoid valves for each hydraulic circuit, depending on the type of HCU. Because the control valves are situated between the master cylinder and the wheel brake units, they can apply, block, or release hydraulic pressure going to the brake units. In a normal non-ABS braking scenario, brake pedal force is transmitted to the master cylinder, and then through the non-energized open isolation valves to the brake units at the wheel. When the signals from the wheel speed sensors show no tendency for the wheels to lock up, the hydraulic pressure from the master cylinder flows freely through the HCU to the brake units at each wheel. When the control unit detects any lock-up tendency, it sends a command current to the isolation solenoid valve for that brake circuit. This current causes the solenoid valve to close, isolating the brake circuit from the master cylinder. That holds the hydraulic pressure between the solenoid valve and the brake circuit constant, regardless of whether the master cylinder hydraulic pressure rises or falls. If the wheel speed sensor signals that excessive wheel deceleration is continuing, the control module commands the dump valve for that brake circuit to open. This reduces the braking pressure by opening a passage from the brake circuit to the accumulator. A pump in the HCU sends brake fluid back to the master cylinder, pushing one or both pistons rearward in the bore and venting to the reservoir. If the sensor indicates that the lower pressure has allowed the wheel to speed up, the EBCM signals the dump valve to close and the isolation valve to open. The hydraulic pressure from the master cylinder is again allowed to apply the brakes, and the wheel is again slowed. This process continues until the vehicle comes to a stop or the driver lifts his or her foot from the brake pedal. In most standard ABS systems, the hydraulic pressure in the brake circuits can never rise above the master cylinder pressure. Types of hydraulic control units: A, B, C, D. Figure 12. The four types of ABS channels. A. Single channel system. B. Two-channel system. C. Three-channel system. D. Four-channel system. There are a number of HCUs that vehicle manufacturers use, and they generally fall into a few categories. The first category relates to how many channels the system has. A channel generally means the number of electrical wheel sensor circuits, and hydraulic circuits a system has. Figure 12. A single-channel system uses one sensor circuit, with a speed sensor typically located in the differential and one hydraulic control circuit to control both rear wheels. Since it is only one sensor, the ABS system has nothing to compare the deceleration to. So maximum deceleration is programmed in the control unit. If the deceleration of the differential exceeds the maximum deceleration, then the HCU will be activated. A two-channel system is similar but uses two separate speed sensors and hydraulic control circuits, one for each rear wheel. The two hydraulic control circuits apply brake pressure separately to the rear wheels. A three-channel system is configured so that each front wheel has its own speed sensor and hydraulic control circuit, whereas the rear brakes use a single speed sensor with a single hydraulic control circuit. A four-channel system uses separate speed sensors and hydraulic control circuits for each of the four wheels. Since these systems have more than one sensor, the control unit not only watches for wheel deceleration that is faster than the programmed maximum, it also watches for individual wheels decelerating faster than others. This gives a more robust ABS function. A. B. Figure 13. A. Single 3-position valve. B. Dual 2-position valves. Another difference among types of HCUs is the number of solenoid valves per hydraulic control circuit. Some HCU units use a single 3-position solenoid valve per circuit. Others use dual 2-position valves per hydraulic circuit. Figure 13. The first position of the single 3-position valve allows brake fluid to flow through the apply port while blocking the release port. The second position blocks the apply port and the release port. The third position blocks the apply port and opens the release port. Thus, the single 3-position valve has all three conditions: apply, hold, and release. The dual 2-position valve style of HCU uses one solenoid valve to open and close the apply port. This is commonly called the isolation valve. When this valve is not energized, the apply port is open. The second solenoid valve opens and closes the release port. When this valve is not energized, the release port is blocked. The EBCM operates each of these valves independently to obtain apply, hold, and release functions. Because there are twice as many solenoid valves, and each valve needs its own electrical control circuit, the EBCM is more complicated and costly to build. Therefore, EBCMs are specifically designed to work with only the specified type of HCU, and EBCMs and HCUs cannot be randomly interchanged. Another difference between HCUs is the type of accumulator used: low pressure or high pressure. Low pressure accumulators hold brake fluid in a spring-loaded chamber when it is released by the dump valves during an EBC event. The hydraulic pressure remains fairly low because an electric pump returns the released brake fluid to the master cylinder when brake fluid in the accumulator reaches a certain point. When the electric pump turns on, the fluid returning to the master cylinder pushes the brake pedal toward the driver's foot, causing the brake pedal to rise. This can be confusing to drivers because it feels like someone is under the dash, pushing the brake pedal back toward them. High-pressure accumulators are used to store brake fluid under high pressure for one of two purposes: to be used as a power booster for applying the integrated master cylinder, or to be used to independently to apply the wheel brake units when the EBCM commands it. When used as a power booster, pressure in the accumulator is maintained by a high-pressure electric pump. The pump is activated by a pressure switch and relay when the hydraulic pressure falls below a certain point. When the pressure reaches the specified upper pressure limit, the pressure switch opens and deactivates the electric pump. The hydraulic pressure is then used to boost the driver's foot pressure on the master cylinder when the driver depresses the brake pedal. If the high-pressure pump fails for any reason, the accumulator holds enough brake fluid at high pressure to apply the brakes 10 to 20 times before the boost is used up. If that occurs, the brakes will still operate but will require much higher foot pressure. Figure 14. High-pressure accumulator. The accumulator used to supply brake pressure to the HCU also uses a high-pressure pump, pressure switch, and relay to maintain an operating pressure of approximately 1200-2700 psi, 8274-18616 kPa, depending on the system. Figure 14. Safety. Be careful to follow the manufacturer's procedures when working on EBC systems. High-pressure brake fluid stored in the accumulator is dangerous. The high-pressure pump pushes the brake fluid against a high-pressure nitrogen chamber, which holds pressure on the brake fluid. The hydraulic pressure is used to independently apply the brakes during a TCS or ESC event. If the high-pressure pump fails while driving, and the hydraulic pressure falls below the pump's specified on pressure, the EBCM will disable the ABS system.